Good evening, ladies and professors. And today we'll be talking about the Math 1D. And with me, we are group 2, and with me you have our teammates, Gia, Nicholas, Zinghan, Asher, and myself, Fahana. So first off, we'll be talking about our problem statement, which is how is the walkability related to the gradient of an area? Next up is the calculated and collected variables. So firstly, we have x, which is the length of walking between A and B, y, which is the length of theoretical straight path between A and B on flat ground, h, the positive difference between the altitudes of A and B, g path, which is the average gradient of the walking path between A and B, g slope, which is the average gradient directly between A and B, and walkability, which is the ratio optimum walking time to realistic walking time. Next up, I'll be passing my time on to Nicholas, who will be talking about the data collection.
Thank you, Fahana. So now I'll be explaining on how we even got to selecting the countries to analyze. So to ensure a comprehensive and unbiased evaluation of walkability across diverse regions, we aim to analyze areas from all over the world and encompassing both the hilly and flat terrains. Our study included countries and regions with varying topographies to capture a wide range of walking conditions. Some examples include the Cameron Islands in Malaysia, Latakia in Syria, Athens in Greece, and Hong Kong. Specifically focused on capital cities such as Bern, Tokyo, Jakarta, and Brazil to ensure relevance and to test our model in environments that are both representative and practical for everyday navigation. The pathways we examined were selected based on how an individual might use Google Maps for basic navigation, focusing on typical walking routes that one might encounter in towns and cities. For consistency, we assume that these paths were accessible and not subject to closures or heavy traffic, which would otherwise complicate the analysis. By standardizing our approach, we aim to create a model that reflects everyday walking experiences while acknowledging that real-world conditions may introduce additional variables such as traffic, road closures, or terrain roughness. This methodology allowed us to focus on the fundamental relationship between gradient, path length, and walkability, providing a foundational understanding that can be adapted to more specific contexts in future studies. I'll be passing on my time to Gia. She'll show you guys how we use Google Maps to gather data. Thank you.
To obtain our data from Google Maps, first we get the location or exact coordinates of the start point and end point. We then enter the destination into the search box in Google Maps and click on directions. We then select a start point with coordinates that are in close proximity to the destination, that is in and around 4 to 5 kilometers radius. We then see the length of the walking path between start point point A and end point point B and enter the value in our table under the column for the x variable in meters. Example here, 0.7 miles is 1290 kilometers. After which, we measure the length of a theoretical straight path between point A and point B on flat ground. This is done by right-clicking the screen at the start point and selecting the Measure Distance option from the drop-down box. Then, place the pointer on the destination and click that point. The distance is shown on the screen. We note this value down in the table under the column with the y variable, again in meters. Finally, the altitude or variable h can be found by clicking on the drop down button near the All Routes Are Mostly Flat text at the left side of the screen. A graph showing the total elevation appears. We note down that value of elevation in meters in our table. Using this raw data, we calculate the slope, g slope, which is h divided by y. We calculate r, the path to distance ratio, which is equal to x divided by y, and our intermediate variable, the path gradient, g path, which is h divided by x. Now Jinghan will be going through the modeling section of our presentation.
Our aim is to find the relationship between the walkability of an area and its gradient. First, we need to calculate walking speed based on gradient using Tobler's hiking function, where W is walking speed in kilometers per hour, and dH over dx is the path gradient. To account for both uphill and downhill travel, we will take the average value, which gives us the function W average. We also define W flat as W average when the path gradient is 0, which gives us the value 5.0367. Now, we can find the expression for the walkability value. We do this by defining two intermediate variables, the optimum walking time T optimum and the realistic walking time T real, for a hypothetical journey from A to B separated by a distance y with a walking path length of x. T optimum can be calculated as the distance y over the walking speed on flat ground W flat. T real can be calculated as the path length x over the walking speed on the path gradient W average G path. Since r is the ratio of path length to distance, r equals x over y, we can replace x with ry. The walkability value is defined as T optimum over T real, which produces this expression involving the independent variables G slope and r. In order to increase the usefulness of this function, we want to simplify the walkability value into a function involving only G slope. We do this by expressing r as a function of G slope. When we plotted r against G slope, we found an exponential relationship between them with an r squared value of 0.7194, which we considered an acceptable fit. Substituting this into the walkability value expression, we get the following expression. Plotting walkability value against G-slope using this equation gives us the following graph, showing an inverse exponential relationship between them with a very high r-squared value of 0.9924. Due to the good fit, we choose this best fit curve as our final expression for walkability value. Using this expression, we conclude that walkability is poorer on hilly terrain, which has a higher gradient compared to flat terrain. Now, Asher will talk about the strengths and weaknesses of our model.
I will now be sharing some strengths and weaknesses on our mathematical model that we've established, right? Some strengths on our model on walkability will include that the model accounts for both path length and gradient difficulty, offering a comprehensive framework for walkability analysis, right? It represents flatness and hilliness as a spectrum based on gradients, enhancing its applicability across diverse terrains, right? Intermediate variables like the path to distance ratio and gradient functions can extend the model's use to other applications, such as energy expenditure or fuel consumption. The model is adaptable for analyzing additional dependent variables beyond walkability. Now, however, no model is perfect. Some limitations that we observed was that simplifications in our calculations limit its scope by excluding factors like traffic conditions, accessibility of amenities, and terrain variability. The model doesn't necessarily account for localized influences such as geography, culture, or historical development of paths. Right. Tobler's hiking function simplifies walking speed but ignores individual differences like age, health, or disabilities. Real-world paths involve complexities like ownership and infrastructure that are not captured by this model. Ultimately, what we have observed and insights that we've taken from our calculations show that the time to walk the optimum path is less than the time to walk the real actual path. What we can conclude from this is that it is faster walking on a flat terrain, less time is required as compared to walking on a hilly terrain where more time is required. And therefore, quality of life is improved living on a flat terrain because the time saved and conserved walking on a flat terrain compared to a hilly terrain, these people can use this time saved and conserved, right, to do something more productive for the remainder of their day. That is what we have found out from our model assessment. Thank you very much and have a nice day.